Okay, we're going to take a look at the design capacity, and we're going to look specifically at the Hunter guide to help us calculate the initial available system capacity, the static pressure and the estimated dynamic pressure that we might have to get us going on our irrigation system. Take a look at the diagram. This is actually figure 21 from the Hunter student guide manual, and you can see your city water source is down here, and that's where you might connect. Coming from that, you would go to the service line, and the service line might be right along here. If you did have a curb stop, it might be somewhere in between here, between the meter and the rest of your irrigation system. You know, we often put an off valve associated with the pressure reducing valve and with the backflow preventer that would be at the point of connection to the house, but sometimes we forget about the service line that would be going from the meter to the house. Now, it may be the same service line that would supply the rest of the house. In that case, it doesn't really matter. You can always shut the meter off. But I have actually installed a lot of irrigation systems that ran on a separate line to get additional capacity from the meter to a different place where we were going to have the point of connection. The other thing you want to look at is the water meter. And of course, most of us are used to looking at water meters. That's usually very close to the property line or somewhere where the city can take a look at it. Sometimes it's buried very deep. I had one when I was living in Utah that was probably the point of connection for me to run to the house was about 5 feet deep. And the water meter was above that, but to tap in was below the frost line to protect it. Then we have the service line coming up to the house, and we come up to the point of connection place that we might actually tap in our irrigation system. From this point on, the other thing we want to notice here is that we do have the highest predicted level of the irrigation system, and we're going to add that in just a minute to calculate our estimated dynamic pressure with the worst case scenario for the dynamic design unit that we need. And so here's a couple of definitions that we want to go through real quick. The design capacity, that's going to be the amount of water that's available for use. That's going to determine how many sprinkler heads or how many drip lines or how many laterals we can connect at the same time. For an awful lot of our household systems, we're talking something in the range of anywhere from 12 to maybe 25 gallons per minute. You know, if we don't have anything else to estimate that, a lot of times we'll just use a hose bib and we'll open it up and we'll see what kind of flow we get out of a hose bib. Now, that's not the best thing to do because a lot of time the hose bib is necked down to 1/2 inch or 3/4, and maybe your actual line coming to the house is much larger. But if you don't have any other easy way to estimate the system, that certainly is one thing a lot of homeowners can do without a lot of additional work. The dynamic pressure is known as the working pressure, and that's the amount of available pressure that we can have to calculate while the water is flowing. It's real important that we realize the static pressure we can measure by attaching a gauge to the hose bib, but we cannot get the dynamic pressure unless the water is actually flowing at capacity. So the dynamic pressure at design capacity is a calculation of the pressure that's going to be available at the maximum system flow rate. So it doesn't do us any good to have a static pressure of 65 psi, and then when we turn it on, the actual dynamic pressure at design capacity drops down to 45, and then we design our system for 60 psi because it's just not going to work. So we got to make sure we check all the available information. The other thing is the flow, the volume that we're going to get in either gallons per minute or liters per minute, or it could be in cubic meters per hour. These are municipal systems that we're used to talking to, so it's going to be a little bit different for us. The dynamic pressure at design capacity, we already mentioned, that's going to be an estimate of the dynamic pressure for the worst case head of the 3 most common landscape irrigation water sources. That's what we've got listed, at least in this particular worksheet. And those are going to be metered municipal, unmetered municipal, and pumping from a well. And we get into that with quite a few rural systems. Well, here we go. We're going to start talking about design capacity. I went outside and dug up my meter so you could see what it looks like. And some of these are buried and have a little cover. And they might also, more than likely, look like something like this nowadays. And you might see that it's hooked up so that it has actually can be read electronically, and most of them nowadays are actually they're able to read without even hooking up to anything. They have they can read them with a meter that doesn't require any kind of connection at all. It's done by the truck as they're driving by. First thing we need to do is to calculate the design capacity with the static pressure where it comes in to the point of contact. Now, we can either measure that if it happens to be available, or if it's not available, sometimes we can call the city and ask them to provide it for us. Most of the time I found that I've had to just simply go to a hose bib at the house and measure. So in this particular picture, if we had a hose bib sticking out of the side of the house right here, and let's say that that elevation was 5 feet greater than our point of connection A, we would have 5 times, if you take a look at this sheet, 5 times the elevation change, and you know this already from the class, is 0.433 psi per foot. So 5 times 0.433 feet is going to be pressure per foot is going to end up being just a little bit over 2 psi. It comes out to rounded about 2.2 psi. That means we can expect there to be a couple of psi difference between here and our point of connection. So if we attach right here to the hose bib and we measure 68 psi, we could expect the available static pressure be somewhere around 70 psi. Now in our example, we're going to just call the city and we're going to ask them. We're going to say, what is our line pressure? And they're going to tell us it's 85 psi at the water source. So now we have a static pressure that we can use to calculate the rest of our system. So we're going to go in here into our design sheet and we're going to put static pressure of 85 psi. Now we need the net elevation change sourced to the point of connection, either uphill or downhill. So let's go back to our drawing here, and according to our example problem, we have an elevation gain of about 12 feet up to the meter and about another 5 feet after that. So we're going to have a total of 17 feet. So the net elevation change is 17 feet. You would just fill this out the same way for any system that you're working on. The pressure change then is going to be 17 times 0.33 in this particular case. That's going to equal the pressure change of 7.36 psi. The static pressure then is going to be 85 minus the 7.36 to give us a static pressure that we can actually start our working with at about 77.64 psi. Now that's the theoretical psi, and of course that's going to change depending upon when you measure it, what's running. You got to make sure that nothing is on in the house, that you have no water running anywhere in the system, and you want to make sure that you measure that when the irrigation system is likely to be running. Most people find that the irrigation system demands that if everybody in the neighborhood is working at the same time are going to be quite heavy, and you may see 10, 20 psi drop. I know in one particular case In one house, we measured somewhere in the neighborhood of about 30 psi drop, and the reason we had 30 psi drop is the two houses that we were looking at were interconnected, and they were both running off of 1 meter. So that meant even though the one house wasn't using it, the other house was, and it made the irrigation pressure that was available for irrigation fluctuate greatly. All right, the next step is we need to actually have some information from the system itself. We need to know the service line, the delivery line, the water meter, and any other valves that we have. So let's go back to our drawing, or back to your actual system if you can, and take a look at it. In this particular case, we have a service line down here that is 25 feet long, and it also happens to be 1 1/4 inch copper. All right, and that's something that you can actually measure. Next is the delivery line. The delivery line is PVC, Schedule 40 PVC. It's also 1 1/4 inch. And the length of that is 65 feet. Finally, we have the water meter, and the water meter in this problem is going to be a 1-inch water meter. And usually you can find that information right on the meter itself. And if you remember in this example right here, if you can see this, that's a 5/8 inch water meter in this particular case. So it's usually stamped somewhere right on the meter itself, so that you don't have to figure out what that is. And in this particular case, we don't have any other valves until we get to the point of connect. So we just need to fill in our data. The service line we said was going to be 25 feet, and the size was 1 1/4, and it was going to be copper. The delivery line was 65 feet, and it was also 1 1/4, and it was Schedule 40 PVC. And then we had a 1-inch. Just write it down here because it's a little easier to see. Meter. Now we're going to take a look at pressure loss through the meter for calculating line number 10. What we do is we take the static pressure at the source up here, 85 psi, we multiply that by 10%. And that's where we get this value right here. And that's going to give us 8.5. Now we need to go to the pressure loss through water meter chart. And there's one in both Rainbird and in Hunter. And I've got that chart here. I've made it a little larger so it's easier to see. And there it is, pressure loss through water meters. And we have a 1-inch meter in this problem. So let's take a look at a 1-inch meter. Now we go down until we find that value, 8.5, that we just calculated. We can go up to, but not exceed 8.5. And as we move down here, I've got that value highlighted. And we can see, we'll lift this up. And you see that after 7.8 is 8.7. So we want to use the 7.8 value, and we'll follow that across. And you can see we've got 36 gallons per minute. So that's 36 gallons per minute in a 1-inch meter for pressure loss. So we're going to write that down here as 36 gallons per minute. For line number 11, volume through the water meter, we can see that it says not to exceed 75% of the maximum safe flow of the meter. And the safe flow of the meter is also indicated on the previous table, pressure loss through water meters. And the safe
pressure on this will be at the bottom of the chart. So we follow the 1 inch line all the way down. There's 1 inch. Follow it all the way down until it stops, and there's 15. We follow 15 across until we hit the gallons per minute here. So 50 is the maximum that we have through the meter, so we're going to write 50 in over here, but it's 75% of that value. And just as we did before, we're going to do the math on that, and we come up with 37.5 GPM. So far, the limitation is the pressure loss through the meter, because we're going to take and we're going to get the lowest GPM of the 3 flow rates for the actual design capacity. But we have one more to go, and this is the velocity through the service line. The velocity not to exceed 7.5 feet per second to the main meter. And the reason for this is to avoid water hammer. So let's take a look now at the velocity not to exceed 7.5 of the service line. The service line that we said was 1 1/4 inch copper. And so I've got that table here. This is copper. We need to make sure that we look at the right columns here, because this one is right here for velocity and for PSI loss through the copper. So we want to make sure we look at the right table. What we do now is we follow down on the velocity. It says not to exceed 7.5 inches. So we follow down on the velocity on the 1 inch, 1 1/4 inch meter till we get down to a value not to exceed 7.5. And there's the breaking point, 737 and 789. So we follow 7.37 across, and we actually come up with a value over here of 28 gallons per minute. So let's take a look at the top there. There's flow in gallons per minute, and there's our value, 28 gallons per minute. So now we have a new limitation. Our new limitation on the system is 28 gallons per minute. So for the design capacity, the value that we're going to write, because it's the lowest of these 3 restrictions, is 28 gallons per minute. Now you might be able to exceed that in some areas, but that's without knowing any more information than we know. That's what we're going to go with, is 28 gallons per minute as the design capacity. The next line is 14. This is when we start calculating the dynamic pressure at design capacity, now that we know the design capacity is 28. So the pressure loss in the service line, we need to know the PSI loss per 100 foot. So let's take a look again at the table for copper, because our service line was copper. And here's that table. And we need to follow 1 1/4 inch PSI loss down. Let's make sure we're on the right table again. So let's move down till we hit that same place we did before, just before it got to 7.5. From the last calculation, we're at 7.96 PSI loss, and that was at our design pressure of 28. Design capacity, 7.96. So we're just going to call that 8 psi. All right, so let's go back to the table. And the pressure loss in the service line is 8 psi per 100 feet. So we have to say 8 per 100 foot, and we have service line length up here at 25. So we'll put 25. So it's 8 times 25 divided by 100, and that's going to come up with 2 psi. For line number 15, we have the pressure loss in the delivery line. We need the psi per 100 foot, and if we recall, we had 1 1/4 inch PVC. So we need to go back to the PVC table, and I have it here for Schedule 40. and I've blown it up again so that you can see it. We have the gallons per minute on this side, and we need to follow the 1 1/4 inch down for the PSI loss, and I've got it highlighted here again. In this particular case, we know our design capacity is 28, so we come down gallons per minute to 28, and we go over until we meet up with our PSI loss, which is going to be right here at 4.25. So PSI loss in a 1 1/4 inch PVC pipe at our design capacity, 4.25 per inch. So we come in here, 4.25 per inch times 65 feet, 2.76 psi. For line 16, we need the pressure loss in the water meter at design capacity. So we go through the pressure loss in the water meter table, and again we follow the gallons per minute flow rate down till we hit our design capacity, which is 28. Then we go over until we hit our 1 inch meter, which is what we have as a 1 inch meter, and that value is 4.6 psi loss through the 1 inch water meter. So I'm going to put that in right here. 4.6. Now we're ready to look at line 18, because we don't have any pressure loss in any gate valves or other devices in here. And other pressures, we have none, so that's 19, which is pressure loss from the source to the point of connection. So we're going to add lines 14 through 18, and if we add these up, we should come up with 9.36. And the approximate dynamic pressure at design capacity, we said that the static pressure up here is 77.64. So we're going to write that in here. We're going to take away the PSI lost from the source to the point of connection, which we just calculated as 9.36. And the approximate dynamic pressure at design capacity is going to be 68.29, or we'll just say it's around 68.3 psi. Now we're ready to estimate the pressure available at the worst case head, and this lets us know that we need the pressure change due to elevation from the point of connection to the highest head in the system. And if we go way back to the beginning here, this is what we had. We had about a 5 foot, we decided to rise in elevation. So that was 5 times 433, 5 times 0.433 for 2.2 psi. So we're going to write that in here. We had 5 feet of elevation change times 0.433, and we said that was going to be 2.2 psi. Pressure total, subtract line 21 from line 20, and we had a total of 68.29, line 20 right there, 68.3, about 66, I'm going to say 66.1 psi. Then what we do for number 23, estimate the pressure available at the worst case head, which is going to be 2/3 of line 22, and that's going to allow for pressure changes in the system, and it's just normal system changes. Dynamic pressure is going to be available between the point of connection and the highest head. So those are going to help take into account the friction losses, pressure losses in fittings, valves, other things, backflow prevention devices, all these kind of things that we haven't added into our system yet, but which can certainly add to the pressure loss. So 2/3 of line 22, which is 66.1, we're going to multiply that times 0.67, and we come up with about 44.3. I'm just going to leave that at 44 psi. So the 44 psi is what we have available. And that means that we can go out and we can find sprinkler heads, or we can find emitters, anything we need that operate at 44 psi or less. Now, what are we going to do with that information? Well, we have the design capacity now that we calculated in line 13. Let's go back here to design capacity. There's our design capacity. Design capacity is the maximum safe flow that we can use for our irrigation system. That's going to be determining how many heads we can operate at one time, or how many emitters. So if we had 3 gallon per minute sprinklers, we could take the 28 and we could divide it by 3, and that would let us know that we better not go over 9 in this particular case. Otherwise we would exceed our GPM of the design capacity. The other thing we have is we have on line 20 now the approximate dynamic pressure at the design capacity, and that means that we can expect to use this as our starting point at the point of connection, and that gives us a guideline when we're doing our irrigation design to complete the total system pressure check and make sure that we've got everything kind of dialed in correctly. The other thing that we have is we have the estimated pressure available right here on line 23 for emitters or sprinklers, and that's the dynamic pressure available for operation of the irrigation system. If there's going to be significant drop in elevation or gain, any of these things could be added or taken away to this value, and we need to make sure that after we do our preliminary irrigation design, we come back and check things and we can fine-tune them. But we certainly have enough information now to get started, and hopefully that's a brief rundown that will get you on the way to designing your irrigation system.